This meeting is now being recorded.
Okay, everybody, we are about to start. Today's seminar is the growing threat of toxic algae and management solutions. So welcome to the Office of Information Management and Analysis OIMA Brown Bag webinar series. The webinar will be strictly 30 minutes event for both presentation and questions and answers. And we also like to remind you that OIMA Brown Bag webinar will be held every month. The next webinar will be on Wednesday, November 30. We normally have it on Thursdays, but the next month will be on November. And those people who are in the building, the room number will change at that time. It is 1510, but we'll advertise that one as well. So the speaker is Terry McNabb. Terry McNabb is the manager of Aquatics, a lake and aquatic plant management firm that specializes in invasive aquatic weed control, toxic algae control, and nutrient sequestration. He is certified lake manager and a past president of North American Lake Management Society, a past president of Aquatic Plant Management Society, and has been active in this field for 35 years. So with this introduction, I will pass up the phone line to Terry to start his presentation. Okay,
yeah.
You can keep on. Yeah. Okay.
Yeah, thank you very much. I appreciate the opportunity to speak to the group today. I've never done one of these before. It's usually you're looking out at a crowd of faces and you get some feedback from that. But anyhow, here we go. I wanted to talk a little bit about, especially in California and some of the other parts of the western United States, we're really seeing increases in toxic algae blooms and that type of thing. So just kind of a overview of what some of the problems are, and then kind of an overview of what some of the current in-lake management strategies or solutions are. He just gave you that, so I'll skip by that. But cyanobacteria is kind of a name for blue-green algae, and they're not technically, they're in the algae family, they're more of a bacteria, but they're thriving in lakes, and they have a competitive advantage as lakes age and get more eutrophic. Lakes are the bottom, the low point on the watershed, so all the nutrients that end up on the watershed can eventually get to the lake, whether it's runoff that comes in pretty quick or if it's soil eroded over time. But basically, once the phosphorus and nitrogen and these nutrients are accumulating in these lake systems, they're getting richer and richer, and obviously, human impacts have some contributions to that as well. But what's happening is these cyanobacteria have a competitive advantage as phosphorus and nitrogen levels dramatically increase in lakes. And it's one of the reasons is, especially from a phosphorus standpoint, is these blue-green algae can fix nitrogen from the atmosphere. So as phosphorus levels go up, you get kind of species shift. They have a competitive advantage. You can kind of see here that just an algae bloom that's windrowed or blown into a line of houses, and you can kind of see what the visual impact is on that. But more importantly, these things all produce toxins. So there's acute kind of and chronic toxins that are developed by the blue-green algae species, and probably the ones you hear about the most are the acute toxins. You have things like dogs dying, from drinking water around a lake. There's been cases like in in New Mexico, where a Fish and Wildlife guy comes out to a pasture with a pond in it, and there's 200 or 300 dead elk there because they drank water out of a lake that had heavy levels of cyanobacteria. So those are kind of the acute toxins. They produce liver toxins. They produce a couple of nerve toxins. And as the populations of the algae build up in the water, they can excrete these things, and that's where the threat comes from. They don't necessarily, you can have a pretty significant algae bloom without the toxins being present, but you generally have to sample for the toxins, to really understand if they're there or not. A couple other ones we'll touch on. There's a kind of a recent discovery of a chronic toxin for waterfowl, and there's some pretty good data now that supports the fact that these things are causing impacts on humans, things like ALS disease and Lou Gehrig's disease, and some of the compounds that are produced by these algae are directly, linked to that now. So just a couple news items from California last year. There's Lake Temescal over in the Bay Area was closed for a number of, they have the lifeguard program there, a bunch of swimming trainings done there. They had to close that whole program down, just from the Bay Area, a couple of dog poisonings. And then you see at the top right corner here, these things aren't necessarily just an issue in the lake. If they flow, the water flows downstream from the lake to, salt water. There's some evidence that you've got some impacts from those standpoints as well. This is a pretty good example of that. Pinto Lake over in Watsonville drains into Monterey Bay. I don't know if you can see it or not. There's right here is where the lake is, and Monterey Bay is over here. And this is a lake that's had microcystis, blue-green algae blooms for a number of years. The water kind of drains down through the system into the lake. And the sea otter, actually, there's been some mortality of sea otters directly linked to the freshwater toxins, microcystis toxins that are coming out of this particular lake. So these things can have impacts beyond where you're seeing them. In the southeastern United States, University of Georgia Department of Forestry has been looking at depths of eagles, and they've linked this back to a couple of reservoirs where there's a new species of cyanobacteria that grows on hydrilla, which is an invasive aquatic weed. And it's kind of a epiphytic. It grows on it grows right on the leaf tissue of the plant. And what they're finding basically is this particular strain of algae, or blue-green algae, the coots and the waterfowl that eat them, they get vacuoles formed in their brain pretty rapidly, like within a couple of weeks to a couple of months. As that happens, they basically can't swim anymore, and the predatory birds like eagles and hawks and things like that are picking them off. They'll eat coots anyway, but if the coot can't swim, for example, because it's got vacuoles in its brain, it becomes easy prey. This is actually migrating right up the food chain, this particular toxin, because the eagles are eating the waterfowl that have been eating the plant, and that's something that kind of is cause for concern, because if something can migrate up the food chain that way, it may also be something that heads towards humans at some point. There's also some recent evidence that chronic long-term exposure of lakeside residents, there's a number of clusters of these things around reservoirs in the eastern United States. There's papers now being published that link a couple of the toxins that are produced by these algae to motor neuron diseases like ALS. There's also a couple of recent journal articles published that are actually documenting the fact that these things can aerosolize. The toxins can aerosolize as wind blows across an infested lake. They're starting to see that these toxins are not just staying in the lake; they're drifting around the community. The other road of exposure there is generally from drinking water. A lot of these are drinking water reservoirs where they're eutrophic. They've had quite a bit of eutrophication over the years, and they're just that's where the drinking water is coming from. So. Lastly, there's another species of algae that's just popped into Southern California. It's been drifting across the southern United States for a couple of years, called golden algae. This particular species, it's invasive. It's primarily a saltwater or brackish species from up around Norway and Sweden. And it's not totally understood yet, but it basically, when an event triggers, and there's starting to be some understanding of that, this little organism, as it blooms, will produce a neurotoxin that's toxic to fish, and you can come out, one day and look at the lake and it looks perfectly good. You come out and look at the lake the next day, and you've got tens of thousands of dead fish all over the surface of it, and that's triggered by the release of this particular toxin that this algae produces. This toxin is specific to fish. It basically stops the transfer of oxygen across their gills, so it doesn't impact any of the other organisms in the lake. And kind of the thought is that it's producing, it's producing this toxin to, generate nutrients for itself. Is kind of one of the theories behind it. So that's kind of the things that are, the reasons you might look at targeting or controlling some of these things. A couple other issues that bump up in California, especially any place you're storing water in a surface water reservoir. Algae can produce, compounds like jasmine and MIB that where the water department, when it brings these things down into the water treatment plant before it delivers it to your home, they have tolerances and levels they're not supposed to exceed of these compounds. So basically, the more algae you have in the water, the more of these compounds might be floating around, and the harder it is to deal with it down at a treatment plant. The next thing that kind of maybe is from a treatment, or potable water consideration is a lot of these. When you chlorinate water, for example, the organic compounds that are in the water can form, with the combination with chlorine, can form trihalomethanes, which are, carcinogenic. And again, another reason why in the reservoir you've got to potentially manage for algae. So there's kind of three prongs to the Clean Water Act. There's a point source program that you guys are probably all familiar with that sets limit discharges of things like phosphorus and nitrogen into lakes. There's also the non-point source part of the Clean Water Act that tries to go up in the watershed and slow down the movement of these things to the lakes. But years ago, there used to be a third leg to the whole thing where EPA funded in-lake restoration technologies. And a lot of this work came out of that. That funding isn't there anymore, and people argue that it needs to come back because a lot of times the money spent in the watershed doesn't, necessarily change what's going on in the lake. So when we get to, down to the lake level, you've got a lake where you're dealing with these kinds of impacts. There's basically two types of technology you can use to go out and target them. One is kind of a reactive treatment. Those are things like algaecides, and I'll talk for a couple seconds about those. The second approach is more of a long-term proactive approach where you're targeting the cause of these algae blooms and attempting to kind of mitigate them. So for reactive algaecide treatment, these technologies are generally used when you need quick relief from something, where a bloom pops up in a reservoir, swimming beach, like Lake Temescal, for example, where you're closed because of an algae problem. The two dominant products that are used for those are generally chelated coppers registered by the Environmental Protection Agency. The one we use quite a bit is called Captain XTR. It's the chelated coppers are designed to keep the copper, which is the algaecidal product, in solution. Copper sulfate precipitates out really rapidly, especially in hard water. And a lot of the treatments done over the years with things like copper sulfate, you have to do them quite a bit more often because the chemical isn't up in the water column very long. You apply this copper sulfate, it forms a precipitate, it sinks, and pretty soon the copper's on the bottom of the lake instead of up in the water column where you need it. Captain XTR and the other chelated coppers are designed to keep the copper in solution. And the XTR actually has a couple of penetrating agents built into it that infuse the copper into the algae, so you can get by with shorter treatments. You get more longevity out of a treatment. Both these things work pretty fast. The other class of algaecides that we're using quite a bit are peroxygen algaecides. These are relatively new. They've come along in the last couple of years. They're real similar to hydrogen peroxide. They break down to oxygen and water, and PAC-27 is the one that we use quite a bit. And then the last thing we'll talk a little bit about is in-lake phosphorus mitigation. So I'm just going to run through a couple case studies where we've done some work to target and remove harmful algae blooms. This particular treatment was done on Silverwood Lake 2 years ago. It's a terminal reservoir for the California Aqueduct. All the water in this lake is just up above this lake's above San Bernardino at about 2,400 feet. All the water in it started at sea level up in the Sacramento Delta and was pumped down the canal and up over the hill and into this lake. And from here it runs down to the Metropolitan Water District of Southern California. There's a recreational focus there as well. But during that summer, there was a bloom that basically triggered the production of these taste and odor compounds and potential violations of their ability to deliver water to the 4 million customers they have. And so this was a project that was designed to kind of come in and reduce the taste and odor compound. And the product we used here was called PAC-27. It was one of the peroxygen algaecides. So This is material that's applied. It's a kind of a powdered form. You see the guy in the boat there kind of pouring a bag into what's called an eductor. That eductor drops the PAC 27 into a water stream that's put out through those cone nozzles you see in the back. So basically, through GPS guidance, the boat moves back and forth across the surface of the lake. And we've treated about 1,000 acres in about a day, 18 hours it took us approximately to get that done. So the objective there, I guess, was to knock down the Anabaena, which is one of the primary blue-green algae species that we bump into. This slide, if you can see it, it basically is looking at cell counts pre- and post-treatment. So the big blue lines on there's 8 sampling sites there. You can see that where the cell counts were pre-treatment. There's bars that are either there or not there because the populations were eliminated by the treatment at all those sampling sites across. You can see there's a pretty dramatic reduction in the species. PAC 27 being an oxidizing agent will oxidize organic matter, so it also has some potential to impact things like toxins that are produced by these things and the compounds that they're trying to get rid of. Downstream at the treatment plant, basically they got a real rapid reduction in the compounds that they were being produced by these algae. They got through basically the rest of the summer with, basically almost 100% reduction from the initial levels of the compounds they were concerned about. So that's an example where a reactive algaecide treatment was done to deal with a problem that took place. The next thing I'm going to talk a little bit about is phosphorus precipitation. Blue-green algae, I've mentioned at the start of this talk, they've got a competitive advantage when phosphorus levels are high. And phosphorus levels are generally high in eutrophic systems. Algae are single-celled organisms, which means they need to get their nutrition from the water column. They're not like a vascular plant that's rooted in the bottom of the lake that can thrive even in oligotrophic lakes, like the Eurasian milfoil in Lake Tahoe, for example. It's a very clean lake, but that plant gets its energy from the lake sediment. So, but these organisms have to kind of go that way. So the idea behind aluminum sulfate, and this is a technology that was developed by EPA and the Clean Water Act back in the 70s and 80s, and it's pretty widespread. It's a sequestering agent, so it captures phosphorus. So it's applied basically to the surface of the lake like this as a liquid. There's 2 passes on the left you see there of the boat. Both of those have the material injected. It forms a flock within a minute or 2 of being injected, and that flock settles to the bottom, and aluminum captures the phosphorus that's dissolved in the water column and sequesters it. Once it's down to the bottom of the lake, it forms kind of a thin barrier on the sediments and prevents phosphorus from releasing from the sediments. So it's kind of a system that goes like that. This particular lake is being looked at this way because of this. They have a TMDL that's been set by the state. They have to reduce the phosphorus levels in this lake. And we're doing 2 treatments a year there, and it's really working pretty well. There is an interim report organized for this. If you can read at the bottom there, it says, to date, the Alum application has neutralized more than 7,600 pounds of phosphorus, an amount equal to the total average load contributed to Canyon Lake by 3 years of urban runoff. So it's kind of going and meeting the goals, and the algae things they've been fighting are down pretty dramatically. There's also a video available if you're interested. You can just go to YouTube, Canyon Lake Alum Treatment. That'll get you right there if you're interested in looking at that. We do run into problems though in that aluminum. If you look at this curve here, aluminum will capture almost 100% of the phosphorus it bumps into, up into about a pH 8.5 or 9. You see how that just crashes to 0 there. Once it's the pH is above that, it just doesn't work anymore. And a lot of the lakes we work with, especially in Southern California, have pHs well over 9. And we're kind of looking around for some newer technologies to help with that. In 2000, we bumped into we took over a project for Orange County. A bunch of their lakes, all of their parks have a lake as a focal point. They're highly eutrophic. They had one of them actually receives reclaimed water, which means the water coming in is well beyond the phosphorus levels that will drive cyanobacteria or blue-green algae blooms. In these cases, alum really wasn't a performance deal for us because of the high pH. We couldn't get it to capture. So we bumped into a product called ThoughtBlock, which was developed by the Australian government's equivalent of our National Science Academy. They developed it through the 80s and commercialized it, and it's been used widely around the world. But basically, it's a modified clay, bentonite clay, where they take the sodium out of the clay and they insert lanthanum, which has just an incredible affinity to capture phosphorus. So it's applied as a slurry over the lake, strips available phosphorus in the water column. Then it ties it up permanently. Once that the phosphorus is captured by the lanthanum, it forms a compound that'll never be available again. So where we see a benefit of using this particular approach is in for 2 or 3 things. When you apply alum to water, the quality of the water has an impact on the performance of the phosphorus sequestration. That isn't the case with ThoughtBlock. The second real advantage is when you put Phosphlock in the water, it will not change the water quality. Up north of you guys, where the water's pretty soft, like in the Seattle area, you're doing things like an alum application. You have to buffer it pretty dramatically because the water's so soft it can't accept the alum without rapid changes in pH. And that can, if you're not buffering it, you can actually, get fish kills and things from dropping the pH too fast. So it's got kind of a neat fit there. You can also calculate the exact phosphorus removal ratio, and so if you know how much phosphorus you've got in the water column, you can kind of target it. Just a couple of case studies. This is one of the parks in Orange County, just before and after shot there. This lake gets reloaded from time to time. It takes reclaimed water, so what we've done is we've put a meter on the inflow, and we can calculate how much phosphorus is coming back into the lake. And we use kind of periodic stripping applications with Phosphlock to kind of keep the phosphorus down and keep the cyanobacteria from forming and impacting the use of the park. Another project we did down there is in the San Diego. It's the only lake Orange County has in the San Diego water quality control region. It's got a real history of cyanobacteria blooms. It's about 50 acres. Issues. You notice the houses around this thing. I was talking a little bit about aerosolizing toxins and that kind of thing, and this is just something we really wanted to kind of get after, and this is a pretty good fit for Phosphlock. So just kind of a picture of what the application looks like. This slurry you see coming out of the boat sinks pretty rapidly. Generally, it goes down through the water column within maybe 10-15 minutes. And it captures all the phosphorus that goes by, and then if you look at the picture on the right-hand side there, you can kind of see how it forms a cap on the sediment. Again, if you dose it to cap the sediment, you can calculate the amount of phosphorus that's present in the sediment and kind of go after it and capture it and prevent it from releasing. So you really get some long-term benefit out of something like this versus a reactive algaecide treatment. Just some quick data from here is a couple years of orthophosphorus and total phosphorus data. Orthophosphorus is generally the dissolved phosphorus that's available to fuel algae growth. You notice that there's a couple years of data there post-treatment. You'll notice that the summer after treatment, the orthophosphorus basically went to 0, and about 40 milligrams per liter is generally considered kind of middle range eutrophic. So we were able to get away from doing algaecide treatments there for some time. If you look at the cyanobacteria data, you can just see that the cell counts are extremely high. For a couple of these different species, post-application, they just didn't exist there anymore. We're catching green algae and beneficial algae that were more up our speed. So that's kind of a quick summary of that particular project. The last thing I want to talk a little bit about is golden algae. Now, this is something that we're starting to see pop up in Southern California. We've got a couple different sites we've worked on it, one in Las Vegas, a couple in Orange County. And you may have seen all the news about a year ago or 2 winters ago, Lake Mission Viejo, which is one of the premier kind of man-made artificial lakes in Orange County. It's about 120 surface acres, had an incredible bass fishery, and they came in one morning and basically all their bass were dead, floating on the surface of the lake. And, well, what's going on here? And we keyed it down to this stuff. So the first time we bumped into it was in the Yorba Regional Parks. That's the 91 freeway you see there down. It's right around Yorba Linda, California, and those parks are in a Santa Ana River channel. You see, and just north of the channel, there's a park there that has about 4 different lakes in it. First sign we noticed were just dead fish. What's going on here? So we basically One of the labs we work with is run by a company called CPRO. They've got a facility in North Carolina where they do a lot of our algae identification. They're pretty well up to speed. And they also have another thing called an algae challenge where they can expose an algae to a number of different algaecides and kind of optimize control strategies. So we sent stuff to them. We got some recommendations back. We made some applications. And we've been sampling this every year since for, almost two and a half years now, and we've never had another occurrence of golden algae in this particular lake. That's not the case down here, though. This is another lake we manage. It's right near Lake Mission Viejo. Mission Viejo is dealing with this thing at almost the exact same time. And there's no boat access to this particular lake. We kind of maybe are thinking that the cells were moving around on waterfall, but again, we found out that we had a golden algae problem when the fish started dying. So we instituted a sampling treatment protocol. We instituted a regular sampling protocol where we ship samples to the algae experts, the ID people, and they give us some data back. The fish behavior prior to dying is they tend to collect on the shoreline. These guys are piled up, and it's almost like they're trying to leave the lake. They're kind of gasping for air. Pretty rapidly, they're dead, and it's just directly due to the fact that they can't breathe because of the toxin in the water produced by these things. So at Rancho Santa Margarita, that particular lake, we haven't really had good success. Well, I take that back. What we've been doing is we've been monitoring this lake, and you can kind of see the algae counts there. The arrows across the bottom are when we've targeted treatment. So we targeted treatment early in January of 2015. We got really good results. There were no golden algae for 6 months or so there, and then for some reason it's kind of popping back up on us. We've targeted it again. And we just had to, come back. They've pretty much lost all their fish in this particular lake, and we're not to the point where we can recommend restocking them because people really don't understand what's triggering these blooms. This is some work that was done by a professor at University of Southern California and presented, and he's looking at this rules for golden algae. The toxin, they're trying to understand when is the toxin produced, how can we maybe better manage these things. And golden algae tend to like really saline water. I think the drought is probably driving up salinity in some of these lakes we're dealing with just because it's evaporating more in reservoirs, and a lot of these lakes, bring the water in, from a reservoir supply, that type of thing. So if this particular algae isn't under stress, there really is no toxin produced. If the stress is very high, then there aren't very many algae cells around, so again, no real toxin. The sweet spot seems to be kind of in the middle there from the research he's done. So we've started looking at maybe expanding from there where we're coming in and making a algaecide application to kill the cells and then following up with a PhosphBlock application to remove the nutrients and kind of try to shove the lake back down into this part of the graph right here where there's no growth present and anything like that. So that's something we've tried. We've had pretty good results, but we're 4 or 5 or 6 months into that particular application. We don't know if it's going to get us where we need to go or not. So conclusions. Cyanobacteria are really an increasing problem in all the United States, and particularly in the western U.S. where lakes are getting more eutrophic. The drought, the drought's evaporation, the water quality is kind of degrading because it's being more concentrated. So we're seeing more and more cases where dogs are dying. There's potential threats, that type of thing. So I just want people to understand that there are some technologies available to kind of come out and selectively target problems where they exist to open water back up. There's also a couple of technologies that are available in lake to really focus on the cause instead of the solution in terms of removing the phosphorus. These things are not to say that the watershed and the upstream contributions that people are trying to control. I mean, this isn't something to get away from that. This is maybe just a third leg or option that's available to people if they get down to the point where they are bumping into water quality problems. So I think I crammed that all into 25 minutes or so. And which I guess the objective, and just hand it back to you guys and see if there's any questions.
Okay, thank you, Terry, for presentation. I think we do have a few minutes if you have questions from the room. And there are some questions that came through the chat box, and we'll answer those ones. You want to go ahead and
Yeah.
answer that?
Let me start with chat. So the first question is, with no reactive treatment, will blue-green algae dissipate on its own?
It's seasonal, right? So it can, it can die back sometimes a little bit in the colder climates during the winter months. We start to get into California, it'll pretty much stick around all year, unless you're at high elevations. You get down into the, LA basin, and you'll see problems, pretty much, all year round. So as long as the nutrients are there, they will out, and they also, their blooms are so thick that they limit the light penetration into the lake. So eventually all the submerged aquatic weed growth that might compete for phosphorus dies off also. So they tend to select for themselves. So as a general answer, I'd say no.
Okay. The next question is, did you mention that cyanobacteria can be either toxic or non-toxic?
Yeah, just because the populations are there and the populations are high doesn't necessarily mean they're secreting the toxins. A lot of times people will just see algae, even if the blue-green algae, maybe think they need to close the lake, but generally what people are doing now is they're actually testing for the toxins themselves. They can send it to a lab, or like in some states have a lab that's all they do. And then they'll base their lake closures on whether the toxin's present, not whether the algae's present. But if the algae's there, they tend to sample more often. So.
Okay. The next question is, what are the impacts from long-term use of the treatment chemicals? What is the buildup in the reservoir sediment?
Okay, so the aluminum sulfate is something that came right out of the Clean Lakes program. The EPA funded all kinds of research that developed that, and they've got really good. It comes incorporated in the sediment over time. It doesn't. Their conclusions were. And this is the U.S. Environmental Protection Agency's Lakes program, their conclusions were there were no long-term impacts from that particular treatment. The PHOSLOC basically just incorporates in the sediment. It's nothing that has any kind of toxicity whatsoever. The lanthanum is actually used as a drug in humans for like kidney diseases and things like that. The peroxygen algaecides, the byproduct of that are oxygen and water, and there's absolutely no accumulation of that whatsoever. Coppers are an element, however. So if you're making a copper application, it's an element. It's going to stay on the lake bottom for some time. They've done a ton of research on this before the EPA registered these things as aquatic herbicides and algaecides, though, and the conclusion is that it's biologically unavailable. So it's not really something that they're totally concerned about. But chelated coppers let you use a lot less copper if that's what you have to do in your particular situation. I don't know if that answers that or not, but
yeah, there are actually a few questions on that, so I think you covered that. So I'll skip down to when using algaecides, do the cyanotoxins post-treatment increase as the algae?
There can be some lysing of the cells that does that real short term, but one of the things the peroxygen algaecides, though, they're just oxidizing agents. They'll oxidize any kind of organic compound they bump into. So you see a lot less of that, and you can actually, like you think back to that Silverwood Lake, the algae cells went way down, but the compounds they were producing went to zero too, and that's probably due to the fact that it was, they were oxidized.
Yeah, Terry, there are several questions. Make your answer a little bit brief, so we'll go through it all as much as we can. Yeah.
Okay, so the next question is, when you precipitate phosphorus, do you also precipitate other essential nutrients that are vital for the ecosystem?
No. Those things both are selective for phosphorus. Alum grabs phosphorus because alum's got a real high positive charge. The phosphorus molecules have a negative charge. So that's attracted and grabbed. The same with the lanthanum in the PHOSLOC. It's targeting phosphorus and nothing else. The idea being, if you take the phosphorus levels down in a lake, the phosphorus is considered the key nutrient in eutrophic systems, and so if you target it, you bring it down pretty much. So.
Okay, the next question is, at what levels do microsystems acutely affect fish? We monitor toxins in Lake Elsinore, and levels are very high, but we have not seen fish kills yet.
We don't. The cyanobacteria, the blue-green algae species, I've never seen a toxic result from, and I don't know that anybody else has either. The toxins are more specific, I think, to mammals. I don't know if the fish have adapted to live on. The golden algae, however, is a whole different animal. but it isn't very widespread yet. It's only in a couple, 3 or 4 lakes down there. So the toxins are more, I guess the fish maybe we don't see fish kills from cyanobacteria. You may see fish kills from oxygen depletion. Plants photosynthesize and they respire at night. If you got big algae blooms, you can see, daily fluctuations of oxygen where it's high during the day and zero at night. So that can cause a fish kill.
Okay, the next question is, when you mentioned reclaimed water being used in the lakes where this is seen, what about the reclaimed water do you believe is contributing? And what type of reclaimed water is used?
I don't know if I can totally answer that, but the phosphorus level, one of the things that reclaimed water generally, when it comes out of a treatment plant and sold to somebody, they don't do a lot of phosphorus removal. They do all the, make sure it's safe for body contact and things like that. But the phosphorus levels can be, 3-4 milligrams per liter, and a eutrophic lake system is anything over 1, right? So, the water that's coming in is really rich in phosphorus, generally.
Okay, next question is, what is the rate of application necessary for the treatment to be effective? What other parameters affect the efficacy of the product?
Okay, if you're looking at Algaecides, the label basically tells you, how much to use. And, for coppers, it's generally about a half a gallon an acre foot. Pack 27 is anywhere from 30 to 100 pounds an acre foot, depends on the rate. The phosphorus sequestering things, though, what you do is you look at, for both alum and phospholock, you look at how much is dissolved in the water column through sampling, and then you can go and figure out, how many pounds are there, and you base your dose on that. And also you look at the sediment release, and you can calculate how much phosphorus is there and target that. So that's a lake-by-lake thing. It's nothing you can give an exact answer to.
Okay. Does the phospholock film that settles to the bottom of the lake affect DO or light attenuation over a period of time?
No, the turbidity is right back to baseline, usually within even almost an hour. So it moves through the water column pretty quick. It doesn't have any kind of it doesn't impact DO in any way, shape, or form. All it's doing is capturing dissolved phosphorus.
Okay, I believe that takes care of all of them.
How about the basic question on how about the effect on that?
We did a pretty extensive, when we did this first phospholock treatment down at Laguna Niguel, the case study I showed you, we did a pretty extensive benthic. There's pretty good data published on that, but most of it's from outside the United States. We did a benthic study, and we hired somebody to do a benthic study, and the conclusion was there wasn't any impact whatsoever.
There, he answered it.
The answer? Yes. Oh, okay. Okay, do you have any question from here? Do you want to shout out?
Yes.
Since you have been sitting here for a while.
Yeah, I just have one really quickly. I work in the Legislative Affairs office here, and we get a lot of complaints from members of the legislature about algae in their districts. This is the first time I've heard that there might be a human health impact other to someone that doesn't even go in the water, to a lakeside resident who is exposed repeatedly, either in the form of through the air or drinking water. So can you and I know the research is still fairly developing on this, but is there any way to quantify, how much exposure is needed for there to be a risk, or how high that risk really is? Is something
I think the papers I've seen, and this stuff's all published like in the last 2 or 3 years, they've confirmed that there's an absolute correlation between one of the compounds that blue-green algae produce and a couple of the, like ALS and Lou Gehrig's disease. So I think they've nailed that down specifically. Then they start looking at pathways, and it's a little bit more, assumption, I guess, at this point to some degree. They think some of this, there are clusters though around, like back in the east in Vermont and places like that, where cities that are getting their drinking water out of a city reservoir that's had algae problems for years, they're seeing clusters of people that have these things that are beyond normal, and they're starting to look at that pretty religiously. I've got those 2 papers that I published on the aerosolize thing that I could send to you guys, and you could make available if you want me to. Those are peer-reviewed, scientific journal articles that, but people are starting to look at this. So I think it's going to be more and more, they're starting to look at it because they've recognized, well, maybe there's a problem here. But so I think the science is going to get behind that pretty quick. Might be happy.
All guests have been unmuted.
No, they're saying even the wind, the birds.
I'll give you a chance for people on the phone, just a couple of questions, because this algae issue is a little bit getting more attention here. You guys have any question from the phone for Terry?
Quick question here. Are any of these examples drinking water reservoirs?
Silverwood is. That's a potable water reservoir for the Municipal Water District of Southern California. There are a lot of reservoirs that treat for algae for these types of things around the state, but I've got some other examples I could probably bring in, but I kind of, you had to talk for 20 minutes or whatever. So
Canyon Lake is.
Canyon Lake, yeah. Canyon Lake is a drinking or potable water reservoir, yep. But it's not online all the time.
Okay, thank you, Terry, and thank you all for participating. Then we will see you next week with another.
Can you tell us how we can get copies of those journal articles that Terry was talking about, please?
Okay, Terry sent it to me, and can you email me? Do you have